right, so here is a little wrap up about friction based on what we did in class. All right, so a couple things from the friction stations. Okay, I'm gonna make this a little bit bigger. Okay. All right, so we found out that surface area, and we didn't, I think, test this one, but also velocity do not affect the force of friction. Okay, that's common things that people think do make a difference, but do not. Okay, the surface area or the velocity do not make a difference to the force of friction. All right, what is important is what we figured out in the lab. Okay, so you have this FF and FN, all right, based on, you know, some kind of block that's being pulled with some normal force, some tension force. That was from the force sensor, normal force, and FG, okay? And then these are the ones that we graphed, all right? I should have asked that question. All right, so you had that, all right? So then the slope of this line comes out to be, say, like 0.3 newtons per newton or something like this, all right? So we're able to graph this FN and FG are equal, and the FF and the pulling force are also equal, all right? Because if this is not moving or moving at a constant speed, depending on in the situation, okay? We had moving at constant speed, so the forces are balanced, all right? Okay, so if we look at this, this is a direct relationship, you see, because it goes through 0, 0, all right? Also linear, but more special than that, direct. All right, so then if we start with our y equals mx plus b equation, we have FF equals 0.3 newtons per newton times Fn plus 0. Okay, so we can just leave that off. All right, this slope here, 0.3 newtons per newton. Okay, so for every 1 newton of normal force, right, how hard those surfaces are pressing together, the force of friction increases by whatever your slope was, in this case, 0.03 newtons. Okay, so that's what the slope is telling us. The harder you press those surfaces together, the more friction there is, all right? And you can press the surfaces together harder by just increasing the weight or the force of gravity of the object by putting more mass into whatever you're testing, okay? Or you could also increase the normal force by actually pushing down on it, right? Anything push or pull down on it, anything that makes those surfaces fit together more tightly, to push together more, is going to increase the friction, right? Which is probably pretty obvious, okay? All right, so this slope that we're talking about, okay, this is what we call the coefficient of friction. All right, and its symbol is mu. It's a Greek lowercase mu, looks kind of like that. All right, and in this case, it was mu kinetic, right? Because this one was actually moving. Kinetic means moving. So anything that's moving will have this mu k value, okay? That's the one that you would choose, all right? So we can see by the equation, the force of friction depends only on the mu and the normal force, okay? So the mu is based on the materials of the surfaces, right? So like there's whole books that you can look up. I mean, now you can look them up online. When I was in college, you had to go to the library and look it up in a book. There's like, you know, rubber on glass, rubber on steel at 20 degrees, you know, steel on copper, whatever. All of the surfaces that could possibly rub together, there's whole books of these values, okay, which basically are obtained exactly the way we did in this lab, okay? And then the normal force basically tells how hard the surfaces press together. Right, the harder the surfaces press together, obviously, the more friction there's going to be, okay? And when the mu is higher, more friction there's going to be, okay? The mu is generally less than 1, okay? Not always, but generally less than 1. So if you do a problem and you calculate and you get a mu of like 3.4, it's probably not right, okay? Very rarely have I seen ones that are greater than 1, okay? They're almost always less than 1, okay? All right, so that's your equation. Okay, and this would really be for kinetic friction, if we want to be very picky there. All right. Okay, so the kinetic friction acts always, if it's moving, that's the amount of friction that acts. It doesn't matter if it's fast, if it's slow, if it's accelerating, if it's slowing down, if it's a Tuesday, if it's sunny outside, it doesn't matter, okay? If the object is moving, it gets that kinetic friction force, all right? The trickier one is the static friction, okay? And then technically, if we rate the static friction equation, it looks pretty much the same, okay? But there's a less than or equal sign, all right? Because as you could see in that graph, right, like when you did the force of the pull, like versus time, it kind of looks like this, right? This is the kinetic friction, okay? And this is the static friction, right? So the static friction is changing as you pull. The harder you pull, the harder it pulls, all right? It's very smart, all right? So the static friction, it does just enough to match your pull to keep the object from moving until you reach that threshold point, right? That would be the equal to part. That's the less than part. This is the equal to. Once you hit this point, right, where it sort of breaks free, sort of, it kind of feels like, right? Then you switch into being kinetic friction, all right? And you can see that the kinetic friction is lower than the static friction in, I want to say every case, but at least almost every case, okay? There might be some weird exception, but probably that we don't worry about, okay? So the static friction will match your pull, okay, or the net force acting on that object to keep it still until that point that you break this threshold, okay? So if it's asking for the maximum amount, that would be the equal to, all right? So like, for example, say that the maximum amount is 5 newtons, all right? If I pull on the box with 1 newton, the static friction will only pull 1 newton. All right. It's not going to pull more than I pull, and then it's going to start accelerating backwards. That's just stupid, right? If I pull with, 3 newtons, it will pull with 3 newtons. Okay. All the way up until the point where I reach that threshold amount, 5 newtons, or whatever I pass that by just a little bit, it will then accelerate and start moving, and then it'll drop to kinetic friction. Okay. And then you have to analyze it differently. All right. Okay, so that's the static friction. All right, is there anything else that I wanted to say? Let me just look for a minute. Graph lab. Oh, the y-intercept. Yeah, I think that's fine. We got that with 0, right? If the surfaces aren't pressing together, right? If the y-intercept is 0, 0, right? If the Fn is 0, then the Ff is 0, right? If the surfaces aren't even touching, then there's not going to be any friction. All right, duh. All right, let's see. Static and kinetic y-intercept. Okay, I think that's everything. All right, so I think that's a quick little refresher on friction.